A ball of mass m is equal to 2 kilograms is thrown vertically into the air with a velocity of 12 meters per second. A constant gust of wind applies a force F is equal to 13I plus 5J newtons on the ball during its flight. What is the velocity of the ball 4 seconds later? So what's happening here? We've got a ball at the moment, and it's being thrown upwards with a velocity which I will call v1, and we can tell using vector notation that v1 is going to be equal to 0I plus 12j. Don't forget that the I and j unit vectors refer to horizontal and vertical directions respectively, and it's of course in units of meters per second. Now we don't know the path of this ball that it's going to take, but let's assume that it looks something like this, and then we'll determine later whether it's actually accurate or not. So let's say the ball's here at its final position, and let's say that over the course of its flight, it's got a force acting on it at every single instant. And that force is given by this expression, F is equal to 13I plus 5J. Now, one thing you need to know about this force is that it's constant. F is not a function of time here, which is quite convenient for us. That means we can draw our forces quite easily, constantly in the same direction with the same magnitude. So it looks just like that, right? This is our ball flying throughout its path, and the force due to the wind is acting on it the entire way through. We've also got the force due to gravity. So let me slow down here. We've got our force due to our wind, and that's given by 13I plus 5J newtons. But we've also got a force due to gravity. So in order to find out which forces are acting on this particle, let me just draw the particle at some instant. We've got our particle at some instant. We've got our force F on it. And we've also got our force due to gravity, which is always going to be downwards, and it's going to be, I'll call it F subscript G. This is our force due to gravity, and we can tell, and don't forget I'm using vector notation, Fg is going to be equal to 0I minus mgj newtons as well, okay? And don't forget that the whole point of this is we're trying to find out the velocity of our ball at some instant 4 seconds afterwards. So this is going to be v2, and it's going to be 4 seconds afterwards. So it's going to be here. And we're trying to find v2, and let's say, we don't know what it is, but let's say it's got a component v2x in the I direction and v2y in the j direction, also of course in meters per second because it's a velocity. Okay, so we're trying to find v2x and we're trying to find v2y, and that will determine our velocity at our second time, 4 seconds afterwards. Okay, so we've got all of this done. Let's see, where do we go from here? Well, the first stop is to recall our impulse and momentum formula. It's the integral of the sum of forces acting on your particle dt is equal to mv2 minus mv1, right? So this is the formula we're going to use. Let's plug in the specific values. Well, the sum of forces is going to be, well, you've got two forces acting on your ball. You've got your force due to wind and your force due to gravity. So this is what it's going to be. It's going to be F plus Fg dt. And that's going to be equal to your mass, which is 2 kilograms, but I'll just write it as m for now, times by v2 minus m v1. This just becomes a substitution game here. So what we need to do is we just need to substitute f and fg, and that'll become, let's see, we've got 13 and 5j. So let me just write the I components first. This will be 13 and then plus 0. Don't forget that the x component of your force due to gravity is 0 because it's purely in the vertical. And then in your y component, you're going to have 5 here. And what's going to be the j component of your force due to gravity? Well, it's negative because it's downwards, and it's going to be minus 2 times 9.81 dt. Now, what are the limits of integration? Well, if we choose to start our experiment at t is equal to 0, that means we finish our experiment at t is equal to 4. So this will be our limits of integration, 0 to 4 seconds. And that's going to be equal to 2 times by v2, which is going to be v2x in the x component, and v2y in the y component. And we're subtracting that from 2 times by, let's see, it's going to be v1, which is 0 and 12. Okay, don't forget it's positive 12 because we're throwing the ball vertically upwards with a velocity of 12 meters per second. Okay, so now what we need to do is we just need to solve this, and we solve this by equating each individual row. So let's start by equating the I units. And let me just quickly resize this so it all fits in. Okay, I've resized it. Now let's equate I units. Well, what we do is we just equate this first row just here, and that's going to turn into, and let me do it nice and slow, it's going to be 13 plus 0 dt, so I'll just write that as 13 dt, with limits from 0 to 4. This is a pretty easy integral to analyze, and that's going to be equal to 2 times by v2x. v2x minus 2 times 0, but I'm going to shortcut that right now and just say nothing. Okay, so that we can solve this quite easily, and that's going to be 13 times by t with limits from 4 to 0, so that's just going to be times by 4. If you do the integration with the limits, you'll see that it evaluates into that, and that's going to be equal to 2 times v2x. And just so you're on the same page with me, I'm actually going to write this extra step here. I probably should do that so I don't confuse you. It's going to be minus 2 times by 0 just there. Okay, well this turns into a pretty easy thing from algebra you've done since year 5, so let's do that. That means v2x is going to be equal to 13 times 4 divided by 2, which is 13 times 2, which is 26 meters per second, right? And notice that v2x doesn't have a arrow on top of it, which means it's not a vector. That's because it's your scalar component of your vector. So this v2x refers to your x component of your velocity vector 4 seconds afterwards. So that's what this is. This is going to be 26, right? If you were to measure this with a ruler, this would be 26. Okay, so we're halfway there. Let's quickly do the same, but in the y direction. So let's equate j units. So this is what it turns into. What we do is we just equate this bottom row of this equation just here, and that's going to turn into 5 minus 2 times 9.81, which is 19.62. Don't forget dt here, and that's going to be equal to 2 times v2y. Don't forget I'm focusing on the bottom row here. And that's going to be subtracted from 2 times by 12, right? Don't forget, bottom row, that's all I'm doing. And then now we just need to simplify this, and this will turn into the integral of minus 14.62 dt is equal to, let's see, this will be 2 v2y minus 24, right? And of course, our limits for the same exact reasons are from 0 to 4. And so when you power through the integration, you're going to be left with minus 14.62 times by 4 is equal to, well, it's going to be the same on the right-hand side. It's going to be 2 v2y minus 24. And when you solve this using simple algebra, you're going to be left with v2y is going to be equal to minus 17.24 meters per second. Okay, so this is your velocity of your particle at your second time, in this case t is equal to 4 seconds, in the y component. So let me quickly redraw this velocity vector so you know what's going on here. This velocity of our particle will look like this, right? This is going to be v2, and if you were to zoom in with that with a microscope, it would look like that, and would have a component in the x direction, which will be 26 meters per second, and will have a component in the y direction, which we just proved was 17.24 meters per second downwards, right? So that means our initial assumption that our particle will actually fall down is correct because its velocity in the y direction is negative after some time. So to reevaluate that, v2y is negative 17.24, which means it's downwards, and v2x is positive 26, which means it's actually to the right. I hope that makes sense, guys. These are components of our velocity at our ball at our second time, 4 seconds after the ball flies into the air.